Welcome back everyone in the second lecture of vector spaces. So in today's video we are going to discuss on these three broad topics. The first is we'll be talking about union of subspaces where we left off in the previous video. Then number two, we'll be discussing what is linear sum, and then we'll be showing that it forms a subspace. Number three, we'll be discussing what is the meaning of linear combination of a set of elements, and then again we'll show that it forms a subspace. So these are the three things that we are going to discuss in this video. So let's start. First of all, this is just an extension of the previous lecture that we had shown that intersection of two subspaces were forming a subspace. Okay, so now I can extend that and say intersection of family of subspaces. Okay, not only just two subspaces, but if I have a family of subspaces, still the intersection will form a subspace. So that's just a property you can keep in your mind. Now the important question is, will the union of two subspaces, will that form a subspace or not? It will not form a subspace. Okay, it won't form a subspace. Now why not? Let's take a quick example. In the previous lecture, you can recollect, I had given this kind of an example where I had taken a set, S set, which was taken from the set of all three-dimensional coordinates where all the elements were real numbers, such that I am making a restriction that x and y coordinates will be 0. Okay, so this is a set S that I am taking, and in my previous lecture I have proved that this is a subspace. Okay, so I won't go into the elaboration of that. Again, if I take a very similar subspace, a very similar one, just I am changing the condition here. Instead of taking x and y to be 0, I am taking, let's say, x0 and z0. So the x and the z coordinate are 0. So it's quite similar to the previous one. So in a similar manner, it's very easy to show that T also forms a subspace. Okay. Now I want to show, will the union of these two things, will it form a subspace? It won't form. Why not? Let's take a quick look. So I am taking an element alpha from the S set. Okay, so let alpha belongs to the S set. So that means alpha will be looking something like where the x and y coordinate will be 0 and z can be anything, any real number. So 0, 0, z1. So this is an element of S where obviously z1 belongs to real numbers. Okay, and I am taking another element beta from the set T. So beta element will be looking like where the x and the z coordinates are 0. So beta will be 0, some y1, 0, where y1 belongs to R. Okay, so I've taken two specific elements from the subspace S and the subspace T. Now, if I take the addition of these two elements, that is alpha plus beta. Okay, so you can see the addition of these two elements will be 0, y1, z1. Okay. So alpha plus beta is looking something like this. Now the question is, will this alpha plus beta, will it belong to the S union T set? Okay, that's one question we need to ask. But before that, I have taken alpha from the set S. So obviously from here I can say that alpha belongs to S means alpha belongs to S union T, right? If some element is belonging to a set, if I increase the sides of the set by taking a union with another set, then obviously that element will be belonging there. Similarly, beta belongs to T. So from here I can say that beta belongs to T by the same previous logic. Beta will be belonging to again S union T, because I have just increased the size of the set by taking a union with another set. So I have alpha and beta both belonging to S union T. Now the question is, will alpha plus beta belong to S union T? Now let's take a look that alpha plus beta, this does not belong to the S set, because for something to belong to the S set, the x and y coordinate has to be 0, and here the y coordinate is non-zero. Similarly, alpha plus beta does not belong to the set, the subspace T, because for something to belong to T, the x and z coordinate has to be 0, and I can see that in alpha plus beta the z coordinate is non-zero. So alpha plus beta is neither belonging to S nor belonging to T. So from this two, I can make a quick conclusion that alpha plus beta will not be belonging to S union T, right? The question that I was asking over here. So alpha plus beta is not belonging to S union T, although alpha belongs to S union T and beta belongs to S union T. So this violates the condition for a set to be a subspace of a vector space, right? For something to be a subspace, if I have two elements belonging to that particular set, then their addition also has to belong to the set. This was the condition for something to be a subspace, one of the conditions, and there was another one as well. But I can see that the very first condition has been violated here. So this means S union T is not a subspace. Okay. So this is an example where we are able to show that union of two subspaces, it is not necessarily a subspace. It might become a subspace, but in general it is not a subspace. Okay. So now this was a counter example. With the help of this example, we made our statement whether it is forming a subspace or not, but now we want to make a generalized proof for it. Okay. So now we want to establish a condition. If that condition is satisfied, then the union of two subspaces will become a subspace. Okay. Now what is that condition? Let's say I have two subspaces P and Q, and their union will be forming a subspace if and only if either P is a subset of Q or Q is a subset of P. Now if we look at this thing in a Venn diagram form, then it's very, very obvious that I have a vector space V. So my first, let's say this is my first condition or this is my second condition. So any one of them has to be satisfied. So if I satisfy the first condition, that means if P is a subset of Q, so that means I have Q something like this and I have P something like this. P is completely inside Q because P is a subset of Q. So obviously you can understand, if this is the case, then P union Q will be the union of this Q set and the P set will ultimately be the Q set again. And if the case was something like this, where the P set is outside and the Q set is completely inside, which is just the second condition, Q subset of P, then from this figure you can understand that P union Q is nothing but the P set again, and it is given in the statement that P and Q are, these P and Q are subspaces. It is already given to us. So since Q is a subspace and P is a subspace, so automatically in either of the cases P union Q becomes a subspace. So the proof or the concept of this statement is very, very simple, but now we will go into the theoretical part behind this. Okay, so we will completely try to prove this as a theorem. Okay, so first it is given to us that P and Q are subspaces. Okay, so this is something that is given in the statement of the theorem. I need to show that the union forms a subspace. Okay, remember it's an if and only if condition, that means it's going to happen from both ways. So first of all, let me consider that P union Q is a subspace, and with the help of that I'll prove that either this is happening or this is happening. So let me assume that let P union Q is a subspace, okay, of the given vector space, whatever that is V in this case. So these are subspaces of V. Okay, so firstly I'm assuming that a union is a subspace. So I need to show that either 1 is happening or 2 is happening. Achha. So let's simplify what 1 is trying to say. 1 is trying to say that if P subset of Q, so P subset of Q means P minus Q will be completely an empty set, because P is completely lying inside Q, right? P is completely lying inside Q. So if I subtract Q from the P set, nothing will be left, so that will be equals to phi. And similarly, this means that Q minus P will be equals to phi. So basically I need to show that either this is happening or this is happening. This is what I need to show. So by contradiction method, let me assume that both of them are not happening, and let's try to see whether any problem occurs from that or not. Okay. So let me assume that let p minus q is not equals to phi, and so the opposite of or would become and, that means both the things will be happening now, and q minus p not equals to phi. Okay. So p minus q not equals to phi, what does this mean? So I have a p set and I have a q set. So if I subtract q, that means if I remove q from the entire picture, if I drag out the q from the p set, some elements of p will be still remaining because it is non-empty. So that means some alpha kind of element will be there in p minus q. And similarly in this part, when q minus p is not equals to phi, that means now if I drag out the p set, if I drag out the p set from the q set, some element, let's say beta, will be remaining in the q minus p because that is not equals to phi. So let's say that let alpha belongs to p minus q and beta belongs to q minus p. Now from the picture only you can understand alpha belongs to p minus q, that means alpha belongs to this red region, means that alpha obviously does not belong to the q set. So alpha belongs to p minus q, this means alpha belongs to p and alpha does not belong to q. Similarly, right from this part, exactly by similar logic, I can say that beta belongs to q and beta does not belong to p. So remember, these two are very important parts because these two things will help me do the contradiction. Okay. Now let's proceed from what we have got here. I have got alpha belongs to p. So let me work on this. Alpha belongs to p by the previous logic which I have done before a few seconds ago, that if alpha belongs to a set p, if I increase the size of the set, it will be still be belonging over there. So I am increasing the size of, sorry, it's not t, it's q actually. So if I increase the size of the set p by doing an union of q with it, alpha will be still belonging there, and by similar logic beta will be belonging to again p union q. Okay. So I have taken that alpha belongs to p union q and beta belongs to p union q. Now look what I have assumed right at the beginning. I have assumed that let p union q is a subspace of V. So we have that in our hand, we can utilize this information. So since p union q is a subspace, that means if I have two elements, then their addition also has to belong to that subspace, right? So from this two I can say that alpha plus beta must belong to p union q, the reason being since p union q is a subspace, right? So I have used the subspace information and I have got the addition of alpha and beta belonging to p union q. Okay. So now let's further use some more information. I have from this thing I can break it up and say that alpha plus beta either belongs to the p set or belongs to the q set, or it may belong to both the sets, but we are not very much interested in that. So let's say that alpha plus beta belongs to p or alpha plus beta belongs to q, right? So either it belongs to the p set or it belongs to the q set, it may belong to both the sets also, does not matter. Okay. Now let me work with this part. Okay. Alpha plus beta belongs to p if this is happening, and I also have that I had taken alpha from the p set right over here. So and alpha also belongs to p. So I can reframe this statement and write that alpha plus beta belongs to p and minus alpha belongs to p, because if alpha is belonging to p and we know p is a subspace, so I can multiply any constant with alpha and it will still belong to p. So let's say I am multiplying the constant -1. So -1 multiplied with alpha becomes minus alpha, that will also belong to p because p is a subspace. Okay. Now I know since p is a subspace addition of these two elements has to again belong to P set. So the addition of these two will be something like this, and which has to ultimately belong to the P set since P is a subspace. So you can see alpha is getting cancelled out and I have beta belongs to P, and you can very well observe that this is a contradiction to this fact which I told you before, that I already knew beta does not belong to P, and right over here I have got beta belongs to P, which is a contradiction. So let's again check the other part and see if we get the same contradiction again. Okay, so now I'm working with that part and I am saying that alpha plus beta belongs to Q and I have beta belonging to Q. So just like the previous part, I'll multiply beta with a -1, and that again has to belong to Q since Q is a subspace. So if I multiply any scalar, it will again belong to the subspace. So now the addition also has to belong to the subspace, and this would give me the beta getting cancelled, alpha belongs to Q, which is again a contradiction to this part that we have already got before. So in either of the cases we are facing a contradiction to our previously known facts. So from here I can say that these two things are giving me a contradiction, okay, which is a contradiction. So this contradiction, why did it occur? This contradiction occurred because I had assumed that this kind of a thing was happening. I had assumed that both P minus Q and Q minus P are non-empty. So due to this wrong assumption, I have got a contradiction. So my correct assumption should have been either P minus Q equals to phi or Q minus P equals to phi. So that should have been the correct assumption. So over here now we will make the correct assumption that therefore either P minus Q is equals to phi or Q minus P is equals to phi. Now this same statement just in form of subset if I write, so this means that either P subset of Q or Q subset of P. So this was the required proof that the union will form a subspace if either this is happening or that is happening. So this is just one part of the if and only if proof. Now we need to go to the other part of the if and only if part, where we need to show that if this thing is happening, then the union will be a subspace. So now coming to the conversely part, conversely let me assume that this thing is happening. So conversely let P subset of Q or Q subset of P, okay, and I want to show that the union will now become a subspace. Now that's very simple to show actually, because if P is a subset of Q, then P union Q would be the set Q itself, because if you look at the diagram, P subset of Q means the set Q is something like this and the set P is something like this. So P union Q will give you the larger set, which is the Q set. And similarly, if this is happening, then P union Q will be the larger set, which is the P set. And it is already given to us that P and Q are both subspaces. So that means in this case, since Q is a subspace, so and that is equal to the P union Q, so the P union Q is a subspace. And in the other part, since P is a subspace, so P union Q is again a subspace. So in either of the cases, we are getting that P union Q is forming a subspace in either of the things that is happening. So this becomes the converse part of the theorem. Now we are going to learn about linear sum of two subspaces. So first of all, we need to know what is linear sum. Suppose I have two subspaces, okay, so I am taking two subspaces, let P and Q be two subspaces of some vector space V. So the linear sum of these two subspaces, it is represented by P plus Q, and it contains all such elements, let's say small p plus small q, such that small p has been taken from the set capital P and small q has been taken from the set capital Q. So this set is called linear sum of the two subspaces P and Q. Okay, so linear sum is basically just the addition of the elements where each elements are taken from the two individual subspaces, and this set of all such elements, that is called linear sum. Okay, so now that we know the definition of linear sum, we want to know whether linear sum itself, whether this itself forms a subspace or not. Okay, so now we will be proving this theorem where we will show that if P and Q are two subspaces of a vector space, then the linear sum P plus Q, that will also be a subspace of that particular vector space. So the linear sum is a subspace. We are going to prove that. Okay, so first of all, it is given to us that P and Q are subspaces. So it is given it is given P and Q are subspaces. So now I am taking the linear sum P plus Q. Okay, so let P plus Q, now as per the definition, it would be small p plus small q, such that small p taken from capital P and small q taken from capital Q. Okay, so let's take two elements from P plus Q. Okay, first of all, before we take two elements, first of all we need to show this is non-empty. Now why is this non-empty? Because since P is a subspace, P is non-empty, and Q is a subspace, so Q is also non-empty. So that means small p and small q elements exists in these two sets, so their addition is going to exist in P plus Q set. So obviously P plus Q is not an empty set. So let me take two elements from P plus Q. Let alpha and beta belongs to capital P plus Q. Okay, so how is alpha and beta going to look like? They're going to look something like this. So let's say that alpha is equals to P1 plus Q1 and beta is equals to P2 plus Q2, where P1, P2 are taken from capital P and Q1, Q2 are taken from capital Q. Okay, so I have taken two elements alpha and beta from the P plus Q set. Now in order that P plus Q forms a subspace, just remember what were the conditions for some subset of a vector space to form a subspace. First of all, we had to show that their addition belonged to that set, and some constant into the element that I've taken, that also belongs to that particular set. So that set we are working with is P plus Q in this case. So this is what we are trying to show. Okay, and the addition of those elements will belong to P plus Q, and some C taken from the field F, okay, C taken from F, that also belongs to P plus Q. So I have defined the alpha and beta elements. So now let's check what happens with alpha plus beta. So you can see if I add up these two things and pair up in this manner, then alpha plus beta would look like P1 plus P2 plus Q1 plus Q2, right? Now small p1 and small p2, these elements have been taken from P, where P is itself a subspace. So you can understand, since P is a subspace, so addition of the elements of P will again be an element of P itself. So I can call this, let's say, some P3, and Q1 plus Q2, since both of them are taken from Q and Q is a subspace, so their addition will again belong to Q. So that means it's going to look something like Q3, where we can say that P3 belongs to capital P and Q3 belongs to capital Q, right? Because P and Q are subspaces. So you can see that alpha plus beta is eventually looking like some element of the capital P set plus some element of the capital Q set, and as per the construction of P plus Q, where we have small p plus small q taken from capital P and capital Q, I can say that this element belongs to P plus Q. So here I can comment that alpha plus beta belongs to P plus Q. So that means the first condition of subspace has been satisfied over here. Now similarly, I want to show the second condition. So I need to take some C from the field. So let's say I'm taking, let C belongs to F and alpha belongs to P plus Q, and I want to check what will happen with their multiplication. So now C into alpha would be C into, now how does alpha look like? It looks like P1 plus Q1. So P1 plus Q1, and if I just separate them out, it would look like CP1 plus CQ1. So if I break them up, so C into P1, this is going to be ultimately an element of capital P, because capital P being a subspace, any element of P multiplied with a scalar C will eventually be an element of capital P, and the same goes for the capital Q set. So I can say that this belongs to the capital P set and this belongs to the capital Q set. So I can just name this as P4 and I can name this as Q4, where I can say that P4 belongs to capital P and Q4 belongs to capital Q. So again you can see that C into alpha looks like some element of P plus some element of Q. So that again satisfies the criteria that this belongs to the capital P plus Q set. So I can say that this implies C alpha belongs to P plus Q. So hence this is the second criteria of subspace. So this was the first criteria and this becomes the second criteria. So combining 1 and 2, I can say that therefore P plus Q forms a subspace. So here we have just proved that linear sum of two subspaces also forms a subspace. Okay, and one quick note that we can just remember over here, that this P plus Q is the smallest subspace containing P and Q. Okay, now just to give you an idea in a Venn diagram what's happening, if this is the vector space V and P and Q are two subspaces, so I have P and Q which are two subspaces of the vector space V, then P plus Q will be looking something like this. Okay, so this will be my P plus Q, where P plus Q is also a subspace which I have proved just now, and it will be the smallest subspace which contains both P and Q. That means if I try to find out any other subspace which contains both P and Q, then it has to be bigger than P plus Q. It cannot be smaller than P plus Q. It has to be bigger because P plus Q is the smallest one. We can also prove this independently, but I am not going into the proof of that. So now we will talk about linear combinations. What is linear combination? Suppose I have a vector space which is V and I have a small set which is S, and let's say the elements of S are alpha 1, alpha 2, dot dot dot, alpha n. Okay, so I have taken a few elements from the set S, which is nothing but a set in the vector space V. Now I want to generate some element with the help of these elements. That element may lie inside the S set, may lie outside the S set. That's not a big problem. Let's say the element which I want to generate, the name of that element is beta. Okay, it may be inside the S set, it may be outside the S set also. Okay, so if I say that S contains only these elements, then in that case beta would lie outside the S set. Otherwise we may say that beta is lying inside the S set also. Okay, so if beta is, let's say it's lying somewhere outside the S set and it's a element of the vector space V, then if beta can be expressed as some linear combinations of these elements, that means some constant into alpha 1 plus some constant into alpha 2 plus dot 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 some constant into alpha n, where all the constants have been taken from the field F for all I equals to 1 to n. Okay, so if beta can be expressed as a linear combination of the elements of the set that I have chosen, then I will say that beta is a linear combination of the elements of S. So if this is happening, we will say beta is a linear combination of the elements of S. Okay, so this is the definition and concept of linear combination. Achha. So now let's look at this theorem. It's saying that if V is a vector space over a field F and S is a non-empty finite subset of V, then the set W, which is the set of all linear combinations of the elements of S, then we have to show that this W forms a subspace of V. Okay, we have to show W forms a subspace of V. And also further we have to show that this subspace is the smallest subspace containing the set S. So what has been told over here, that I have a vector space, let's say this is my vector space V, and I have a set S of, it's a non-empty and a finite set. So I have a set S which contains some elements, let's say alpha 1, alpha 2, dot 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 going up till alpha n, and I have to show that if I take the set W, which is the set of all linear combinations of the elements of S, so that means W is something like this, which obviously is going to contain S. I'll tell you why it is containing S, and it is created by taking all the possible combinations of the elements of S. The W set has been created. So first of all, we have to prove that this W is a subspace. This is the first thing we have to prove, and the second thing we have to prove that this W is the smallest subspace that contains the S set. So if I take any other subset, any other subspace which contains the S set, then it has to become bigger than W. Okay, so if I take any other subspace containing S, it will automatically become bigger than W. It cannot be smaller than W. So these are the two things we have to prove in this theorem. So first of all, let's create our S set. Let's say that let S equals to alpha 1, alpha 2, dot 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 alpha n. Okay. So I have taken my S set. Now W is the set of all linear combinations of the elements of S. So now I am creating W. So therefore W equals to C1 alpha 1 plus C2 alpha 2 plus dot 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 Cn alpha n, such that each of the constants have been taken from field. Okay. So I have created W. So W is the set of all possible linear combinations of the elements of S. Now I told you that why will W contain S? You can take, for example, if the value of C1 is 1 and the rest all other constants, if I take them to be 0, if all the constants are 0 except the first one, if I take C1 as 1, then if you put those values over here, you can see you will get C1 1 means only alpha 1 will be remaining and rest of the things will become 0. So W contains the element alpha 1. Similarly, if I take C1 to be 0, C2 to be 1 and remaining C3 onwards all the elements to be 0. Okay, so again if I take it in this format, except C2 if all the other elements are 0, so in place of C2 I'll put 1 and rest everything will become 0. So then again I'll get alpha 2. So again I can see W is containing alpha 2. So in this manner if I keep on going, I'll get all the elements of S. So W automatically contains all the elements of S, and it contains even more elements. So now if I take other elements to be non-zero, other constants to be non-zero, I'll get some combination of the alphas and some new element will be created. So that's why W is bigger than S, obviously containing S, and now I need to show that W forms a subspace. Okay. Achha. So again let's recollect that if I want to show that something is a subspace, I need to show that the addition of the two arbitrarily taken elements from that set is going to belong to the set, and some constant times an element of the set is going to belong to that set, right? So these were the two necessary and sufficient conditions for a set to form a subspace. Okay, so let's take an alpha element. Okay, from W I'll be taking an alpha element and a beta element. So first of all, whenever I've created a set, I need to say that it is non-empty. So I can say that here W is non-empty as alpha 1 belongs to W, because if I take C1 value to be 1 and all the other constants to be 0, I can obviously take that, because all the C elements are taken from field, which is the constant set. I automatically get the element alpha 1 which belongs to W. Acha. So now I am coming to this property. I am saying that let alpha comma beta belongs to W. So I need to define how these elements are going to look like. Whenever I take an element from W, it looks something like this. So I can say that therefore alpha equals to, so I'll just change the name of the constants. If I take some specific constants for C1, C2, Cn, then I get the alpha element, and some other specific constants I get the element beta. Okay, so I'll just take some specific constants. Alpha equals to, let's say, R1 alpha 1, R2 alpha 2 plus dot 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 Rn alpha n, where all the R suffix I elements are taken from field. And for the beta element, again I'm changing the constant. Let's say S1 alpha 1, S2 alpha 2 plus dot 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 Sn alpha n, where all the S suffix I elements are taken from field. Okay, so I have considered two elements from the W set. Now I want to show their addition also belongs to the W set. Okay, so I am taking the addition. Now alpha plus beta. So if I add them pairwise, okay, if I add up the first pair, if I take alpha 1 common, I'll have R1 plus S1. Similarly, if I take the second pair and if I take alpha 2 common, I'll have R2 plus S2. And if it goes on this way, finally if I take alpha n common, I'll have Rn plus Sn. Now you can see each of the R and S kind of elements have been taken from field. So their addition, R1 S1, R2 S2, Rn Sn, all these additions are also further constants which again belong to the F set. So I can say that this entire construction is some constant into alpha 1 plus some constant into alpha 2, and like this some constant into alpha n, which is the construction of the capital W set. So automatically this kind of an element is going to belong to W. The reason being, since R suffix I plus S suffix I, these kind of constants, they belong to field for all I equals to 1 to n. Okay, so the first property of forming a subspace has been done, that the sum of two randomly taken elements is belonging to that set. Now I need to show that alpha into some C quantity, some quantity taken from the field, their multiplication is also going to belong to W. So let's start with that part. So C into alpha would be C into, now alpha looks like R1 alpha 1 plus R2 alpha 2 plus Rn alpha n, and if I just multiply the constants inside with all the respective elements, I would get C R1 alpha 1 plus C R2 alpha 2 plus C Rn alpha n. So again, by same logic, you can observe that these are again further constants, because C was a constant taken from field, and R1, R2 up till Rn, these are also constants taken from the field. So multiplication of two constants would further be another constant. So again this looks like some constant into alpha 1, some constant into alpha 2, and like this some constant into alpha n, which is how the W set looks like. So I can say that C alpha belongs to W, which is again my second required criteria for W to be a subspace. So combining this one and this one, I can say that therefore W forms a subspace. So that was my first part of the theorem. So I have just now proved that the linear combination of elements of any set taken from the vector space, it forms a subspace. Whatever set I take, it has to be just finite and non-empty, obviously non-empty and finite. If I take the linear combination of all the elements of that set, it's ultimately going to form a subspace, and that subspace obviously contains that set, which is the Venn diagram that I have drawn over here. So now coming to the second part of the theorem, the second part said that this subspace that I have created, this subspace is the smallest, okay, it is the smallest subspace containing the set S. That means the thing which I was saying, if I take any subspace P which contains S, it has to become bigger than W. It cannot be smaller than W. Okay, so let's try to prove that now. So I can refer to this figure over here, that if this is V and this is S, and let's say this is W. So what I want to show is that whenever I will take a subspace containing S, it has to be bigger than W. Okay, so if P is a subspace containing S, subspace containing S, then it has to be bigger than W. Okay, and W is subspace, or I would say W is set of all linear combination of the elements of S, which obviously forms a subspace, which I have showed just now in the part above. So this is what I want to establish. Now you can see that for something like this to happen, whenever I will take an element from W, okay, I'm taking an element from the blue set, which is the W set. Whenever I take an element alpha from W, if this Venn diagram has to happen, then every time I take alpha from W, you can see automatically this alpha belongs to the P set also. Okay, because P is a set containing W. So any element taken from W obviously belongs to the P set. But the vice versa is not true. That means if I take any random element from P, it may not belong to W, because that element might lie somewhere over here. It is in P, it is in the set P, but it is not in the set W. Okay, so if I am able to establish this for any arbitrarily chosen alpha, so whenever I arbitrarily choose an element alpha, and if choose alpha from the set W, and if that automatically belongs to the set P, then this kind of a thing would be established. Okay, so let's try to show that alpha taken from W would imply alpha belongs to P. And so I have already defined alpha before. So again I'll say that let alpha be looking like R1 alpha 1 plus R2 alpha 2 plus dot 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 Rn alpha n, such that Ri has been taken from the field. Okay, so it's just the same way I have defined it before. So now I want to show that this also belongs to the P set. This is what I want to show. Okay, Achha. Now P is a subspace that I have already declared, that P is a subspace which contains S. Okay, so if P is a subspace containing S, and S contains elements like alpha 1, alpha 2, alpha 3 up till alpha n, S contains all those elements. So you can see alpha 1, alpha 2 dot 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 alpha n, all these elements belongs to S, implies alpha 1, alpha 2 dot 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 alpha n, they also must be belonging to P, because P contains S, so every element of S is definitely an element of P. Okay, so now we know that since P is a subspace, okay, it is told to us that P is a subspace, that is what we have considered. So if P is a subspace, then R1 alpha 1 would definitely belong to P, because that's a criteria for something to be a subspace. Any constant multiplied with an element of the subspace has to belong to the subspace. Similarly, R2 alpha 2 would belong to P, and like this Rn alpha n would belong to P, where all the Ri have been taken from the F set, which is the field. Now since P is a subspace, so if these elements belong to P, then their addition also has to belong to P. That was property number 2 of subspace. So therefore from here I can say that R1 alpha 1 plus R2 alpha 2 plus dot 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 Rn alpha n, the addition of all these elements also has to belong to P, and you can see that this element is nothing but the alpha element, which was R1 alpha 1 plus R2 alpha 2 plus Rn alpha n. So from here I can see that alpha belongs to P. So I had started with alpha belonging to W. Okay, this is from where I had started, and this is where I have reached, and this was exactly the thing that I wanted to show. So I have done that. Therefore alpha belongs to W implies alpha belongs to P, and as I told you before, this means that W is a subset of P. So that means whenever I choose a subspace containing the set S, it is going to be bigger than the W set. So this means W is the smallest subspace containing S. Okay, so that's the proof of this theorem that we have done. Achha. From now on, let's get used to one abbreviation. This W set, in this particular theorem, this W set was a set of all linear combinations of the elements of S. So from now on, whenever I will have a set S, let's say that is alpha 1, alpha 2, dot 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 alpha n, then the set of all linear combinations of the elements of S, that means C1 alpha 1 plus C2 alpha 2 plus dot 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 Cn alpha n, such that all the Ci's belongs to F. So this entire set, which is created by linear combination of the elements of S, we are going to call this L of S, which means, or which is called linear span of S. So now on, this is going to be the abbreviation that we are going to use. So linear combination of elements of any set is going to be written as L of that set, where L of that set implies linear span of that particular set. And we have already shown that this L of S thing, it forms a subspace, and not just any subspace, it forms the smallest subspace containing the S set. Okay, so this is the abbreviation which we are going to follow from the next topic onwards. Okay, so before moving on to the next topic, let's do one problem based on linear combination that we have done just now. So alpha is given to us, beta given to us, gamma given to us, and delta given to us. These are all three-dimensional coordinates taken from R3. So we need to examine two things. The first one, whether alpha is a linear combination of beta and gamma or not, and beta is a linear combination of gamma and delta or not. So these two things we need to verify. So let's quickly look into the first one. If alpha has to be a linear combination of beta and gamma, then alpha must be represented in this format: some constant into beta plus some constant into gamma. So if this expression is possible for some constant C1 and C2, obviously taken from, instead of writing field, we will be writing real number, because right now we are working with real numbers. So if this relation is possible to write, then only we can say that alpha is a linear combination of beta and gamma. So I would start by saying that we can write this. Now let's check we can actually write it or not. So if I put in the values of alpha, it is 435 equals to C1 times beta is 013 plus C2 times gamma is 211. So that means 435 equals to, if I just add up the x coordinates, it would be 0 times C1 plus 2 times C2. Then if I add up the y coordinates, it would be 1 times C1 plus 1 times C2. And finally, if I add up the z coordinates, it would be 3 times C1 plus 1 times C2. So now if I compare the x coordinate elements, I am getting 2 times C2 is equals to 4, and that means C2 would be equal to 2. Similarly, if I compare the y coordinate, I would get C1 plus C2 equals to 3. We are getting it from this comparison, and I'll just plug in the value of C2 that I've got over here. So from that I will get C1 equals to, if I put 2 over here, C1 would be 1. And finally, comparing the z coordinate, I will have 3C1 plus C2 equals to 5. So now if I plug in the value of C, I don't need to plug in actually, I can just verify whether it's satisfying or not. So if I take C2 value to be 2 and C1 value to be 3, so these two values are going to satisfy the third equation. So the third equation is satisfied by the values I have found out from the first two equations. So this value of C1 and C2 exists, and these are real numbers. So hence this expression is valid for the value of C1 equals to 1 and C2 equals to 2. So if this expression is valid, then obviously alpha can be written as a linear combination of beta and gamma. So that's established. Coming to number 2, now we need to check whether beta can be written as a linear combination of gamma and delta. So again, I'll start by saying that let beta can be written as C1 times gamma plus C2 times delta. So I will plug in the values of beta. I have beta value to be 0, 1 and 3. So 0, 1, 3 plus C1 equals to C1 times gamma value. Now the value of gamma is 2, 1, 1 and delta is 4, 2, 2. So 2, 1, 1 plus C2 times 4, 2, 2. So again, if I equate it in the same way as before, the x coordinates, I'll get 2C1 plus 4C2, C1 plus 2C2 and C1 plus 2C2. So just from these two observations, C1 plus 2C2 is equals to 1 and C1 plus 2C2 is again equals to 3. Okay, so I have got, by comparing the y and z coordinates, that C1 plus 2C2 is equals to 1, and again in the second comparison C1 plus 2C2 equals to 3. Now is this possible? I have the left hand side same in both the cases, but my right hand side is different, so that's not possible. So this system of equations is inconsistent. Okay, so that means no possible real values of C1 and C2 exist such that both these equations can be satisfied. So hence the conclusion is that beta is not a linear combination of gamma and delta. So we cannot express beta as a linear combination of gamma and delta because such constant values are not possible to find because we are facing an inconsistency. Okay, so that's the concept of linear combination. See you in the next video where we'll discuss further details about vector space.